I'm very happy to introduce Russ Parsons as our LOF&BE webinar speaker for this month. So I'm Sarah McAllister. I host these with Sam Manzello and Sayaka Suzuki. And I guess without further ado, I'll start into the introduction with Russ. So he is one of my coworkers. He is a research ecologist with the Fire, Fuel, and Smoke program at the Rocky Mountain Research Station with the Forest Service in Missoula, Montana. He got his BS in forestry from UC Berkeley in 1992, go Bears, and then worked for several years in fire and resource management with a number of different agencies. He got his master's degree in forest resources at University of Idaho in 1999 and joined the Fire Lab in 2000 as a remote sensing and GIS analyst, later becoming a research ecology after completing his PhD in forestry at the University of Montana in 2007. Yeah, he does a lot of great work, and we're going to hear a lot about it in the next hour. So I think without further ado, I will let Russ go ahead and get going.
All right. Well, Sarah, thanks so much. And thanks to all of you for being here. It's exciting for me to get a chance to talk with this group. So yeah, I'm going to be talking about some of our work putting together a system that facilitates modeling fuels and fire with an application mostly targeted at prescribed fire and fuel treatments. And I'm really very lucky to work with some really great partners. Rod Lynn at Los Alamos, Kevin Hires with the USGS and Tall Timbers, Lucas Wells with Holtz Forestry, Daniel Rosales at Tall Timbers, Anthony Marcosi at University of Montana and Holtz, Karen Riley with U.S. Forest Service, another colleague of Sarah and I. Sarah Flannery works for me at the Fire Lab. And Jesse Johnson, University of Montana, Chad Hoffman at Colorado State. So anyway, I'd also like to acknowledge that this work that we're talking about today has been the product of several years of work, and we wouldn't have been able to get there without support from various people such as the Joint Fire Sciences Program, the NWCG, the Western Wildland Environmental Threat and Assessment Center, and CERDIP, a program within DoD. Okay, so let me jump into this. This is probably preaching to the choir, but in the Western United States, particularly in the last years, we've seen quite a lot of really complex things going on with our fuels, often aggravated by climate change. This is going on elsewhere as well, of course, but we've seen really pronounced drought. That in combination with other climate factors has brought about some epidemic beetle attacks, which have wiped out large swaths of forests. We also have a continuing problem with invasive species like this cheatgrass, which can really change the dynamics of the surface fuel continuity. And ultimately, all of these things are making fuel and fire management higher risk and lower certainty than we've had in the past. And of course, we know that with the fire behavior triangle, fuel is the only factor that we can actually directly influence. So we are usually constrained by not being able to change topography or weather. We can change what conditions of weather we choose to burn in for prescribed fire. So that's one of our big ways we can change the picture. But fuels are the one thing we can actually manipulate. So in the US, we're seeing a shift now where we're moving from a almost completely suppression-based paradigm in fuels management to considering these proactive approaches like prescribed fire and fuel treatments as a better way to go. And a lot of analysis shows that that's just necessary, that we can't suppress our way out of our problems. Of course, prescribed fires are pretty common in many parts of the world, but in other places they're not as common. They do represent fires that are lit by managers under conditions that they choose with or without fuel treatments done beforehand. So one of the challenges that we face with fuels management for large areas, such as in the US, is that we need spatial data to be able to make strategic decisions. And so we have national scale data sets that are primarily developed with Landsat imagery that are developed through what we call the Land Fire program, which is another partnership program between the U.S. Forest Service and USGS and other agencies to map the whole country at 30-meter data. But one of the challenges that we often run into is that the actual detail of what fuels really mean for fire is often really specific at a very local scale. So there's this rather substantial scale gap between what we can walk around and measure on the ground and what we represent at large areas. And this has always been a challenge, and it will always continue to be a challenge. But anyway, it's part of the rationale for some of the work that we're talking about today, is to see ways that we can transcend that scale gap. So, of course, while our national mapping systems in the US are primarily driven by Landsat imagery, increasingly we have greater availability of these more detailed data sets, such as high resolution imagery, sometimes multi-band with near infrared or mid-infrared bands. And then particularly airborne LiDAR, which captures 3D structure of forest fuels and can be processed to identify individual trees or groups of trees within a forest and to measure their heights and things like that. So this is new data. There's been a lot of it collected in the last few years, but it's still not used to full effect within the Forest Service. So that's another one of our goals, is to make it better, make it easier to use the data that's being collected out there. And then going in finer detail, we have ground-based LiDAR scanning with terrestrial LiDAR scans and larger than plot areas, but smaller than landscape areas that can be mapped with drones or UAS. And these are really detailed data sets that so far have not really had a way into our national mapping systems because they're just too fine detail. Of course, LiDAR and UAS data give you point clouds, which can be, which give you a 3D view of the data. This is a example from some gridded TLS scanning that was done in our field site in Oregon. And one of the advantages of point clouds is that they can be summarized to voxels. And voxels are an efficient way of representing data across 3 dimensions. So when we're dealing with 3D fire models, there's a natural inclination to try and use this kind of data. So as our national systems are driven by relatively coarse data, our national fire modeling systems are also fairly simple. They're fast running, but they're relatively low detail. So essentially, if you're looking at this kind of fuel bed, which you'd find in the Great Basin, for example, you find these really dense patches of individual shrubs or small trees, often with little fuel continuity on the ground, but patchy fuels, which are very, very complex, these fuel beds. But in terms of representing them for our landscape scale national tools, these are homogenized. So all of that kind of variability is lost. And the models that we use, which are based in the Rothermel model, basically assume continuous and homogeneous fuels at the scale of the pixel. So this makes it challenging when you're looking at proactive approaches that look at fuel changes, because the sensitivity to the actual fuel change can be fairly limited when you're going through that process. So we're used to collecting detailed data in the field at the plot level for forestry, and we have models like you see here. The forest vegetation simulator is a common empirical statistical model used to predict individual tree growth, and has a lot of tools built into it for looking at silvicultural fuel changes and things like that. But when we try to connect that data to our operational fire models, we go through kind of a bottleneck where the individual tree detail that we have there just really can't be used by those models. So again, it's not an issue with our operational models when the goal is to predict in a general way where a fire is going to go in a short period of time, but it becomes limiting when you want to be more proactive and look at what things you might do to change outcomes in the future. It's also relatively limited in its ability to capture natural disturbances that sometimes modify part of a forest or part of the fuels, but not all of them. So currently when we do fuel treatment analysis in the US, it's using Rothermel-based tools. So FlamMap and Farsight and FS Pro, you've probably heard of. Those are all actually implemented in a tool that is usually is used pretty widely now, that's called the Interagency Fuel Treatment Decision Support System. So we love our acronyms here in the US. But essentially what is going on there is that if you have an area, you have your 30-meter cells from, driven by Landsat data, and let's say you have an area that you're treating, well, the treatment consists of reassigning those fuel models at those 30-meter scales. Okay, and the most common data people use to describe that is this Scott and Bergen 40 models, and these are part of the Landfire data. And then the models that I've been working more with in the last several years are these 3D fire models that are really pretty powerful for looking at different aspects of fire behavior, but they're also very computationally intensive. But one thing I think that's interesting to note is that the Navier-Stokes equations were developed in 1822. So this year, 2022, is exactly 200 years. And think about that for a second, that math was developed before there were any computers to run those calculations. That's pretty incredible, right? But anyway, so there's an increasing range of these kind of models, and here's an example where a real-world fire simulation was carried out in Australia, and then reproduced quite well with FDS in this model, in this paper described by Ruddy Mel. So there's a lot of opportunity for these models to give us insights about fire behavior, and particularly in things where we're looking at the interactions between fuel changes and fire behavior. These models give us a greater range of insight. So in 2018, we came up with a prototype system that we called StandFire that links plot data at the basically small landscape, well, not very big landscape data from plots, and links with the FVS model, so we can look at forestry changes and things like that. And we hooked it up to models like FVS and FireTech. So this is an example. In this case, the simulation is done with FDS. And actually, I should say it's WFDS. This is the version of FDS that Ruddy Mel's been working with. So this is an untreated stand, and then each one of these are different treated cases that are derived from that. So they represent a spatially explicit thinning case built from this initial case. And what you see here is that really all of these treated cases all knock the fire down on the ground. So they lose a lot of that continuity in the canopy fuels. And so the differences between these are not that great, but if we were to run it at a different set of winds or different fuel moistures, we might see some more dynamic differences between them. So as part of our development with StandFire, we developed a series of metrics that look at what happened with the simulation to make it more usable for managers. So for example, we can summarize heat and fuel consumption, et cetera, over time. And we can also look at, we can link the individual trees. In this case, we're looking at this area right here as an area of interest. We can look at the probability of mortality for each tree based on, in this case, based on fuel consumption, as opposed to scorch, which would be the better mechanism. But this would be the pre-treatment case, and this is the treatment case. And what you can see is, of course, there's far fewer trees in the treated case because it got thinned, but the prediction is that most of those trees would survive that fire. So this is an important feedback as we look to methods that are going to enable us to get resilience in our forests. So if we can look at a fuel treatment, model it beforehand, and know with some degree of certainty or some level of accuracy that our treatment and prescribed fire combination will achieve our goals, it's really helpful. So Anyway, based on our stand fire development, these last year and a half or so, we've been working on this new system that we're calling fast fuels. So fast fuels is still totally in development, but there's a few cool things we can show you about it. So the bottom line is that we're trying to get past this problem where these detailed fire models haven't had any data to run with. So they've been fundamentally limited by unavailable data. So where we've had the 30-meter wall-to-wall data for the whole US and the operational models that run on it, we haven't had a corresponding data that these models can be used with. And really, each use of these models has been essentially a one-off use for a small area. So we were trying to get past that limitation. So fundamentally, fast fuels is intended to advance fuel treatment and prescribed fire science, and then provide a means by which we could accelerate the mapping update cycle. Because right now, our land fire data is updated on at least 2 and often 4 to 5 years between maps. And you can imagine that with all the fires that we have and the disturbances and climate change and everything else, that is not a close enough interval for updating our fuels maps when decisions are made around those fuels. So updating the map cycle, and then particularly providing a pathway by which more detailed data can be assimilated into fuels maps. And then I'll tell you more about this in a minute, but the basic construct of fast fuels is that it's cloud-based and automatable, and it's a data on demand model fundamentally. So it operates on a relatively small spatial window. So you're not having to run everything for the whole country all at once. You can focus on an area. That also lends itself to this integration of data, of more detailed data for that area when it's available. And then the last goal of fast fuels is to enhance cross-model connections. So we know that there's many processes that we're interested in, not only in fire, but also in ecosystem function that relate to the more detailed structure of fuels and forests, and where we can bring good science to bear if we have a place for those things to connect. So fundamentally, fast fuels is kind of intending to be a series of Lego blocks in which different models can connect using the same data. And we kind of refer to it as a superhighway connecting fuels data to fire models. And another thing to mention is that it's intended to be model agnostic. That is, we want to support all of the fire models with this platform. So just a quick overview of how this works. Essentially, one of the key pieces that makes fast fuels work is some really excellent work done by Karen Riley, one of our partners at the Fire Lab, and Mark Finney and other folks, where they developed this thing called the tree map layer, which is a imputed map that basically takes inventory plot IDs from our large scale national plot data, which is FIA plot data, of which there's hundreds and hundreds of thousands of plots. And then they built a system that imputes this back to the landscape as plot IDs being the measured quantity for a given pixel. That then links to a tree list, which we can then use our stand fire logic with. Since our stand fire logic is built around tree lists, this is a natural connection. So what we do is we then we can do all these things with that. So we take the tree lists and we apply the same kind of setup that we've done with stand fire. We place trees, we voxelize them, we produce outputs that are inputs for other fire models, and then we have another set of tools that fit around that. So this is an example data tile. I think it's actually a kilometer by a kilometer, but it shows example 3D data from fast fuels. And you can see that the process that we have here, the underlying data are plot level data that are actually quite far apart. They're actually multiple kilometers apart, and they're small plots. So the imputation process that Karen Riley does, which brings a tree list to a pixel, we then place trees within the thing to give a synthetic representation of that fuel in 3D, but it gives us the advantage of wall-to-wall data that has plot level like detail, but over large areas. So here's a link that I'm going to print here. And I wonder if Sarah, if you might just copy that into the chat and people could play with this while they are looking at this.
They'll do. Working on
Okay.
it.
I'm like really bad at doing that in the middle of a talk, but if you might help me with that, it would be great. So yeah, so you might recall that I said that fast fuels is automatable and it works on a data on demand concept. So for a given area, it's going to calculate that data. It's going to draw in the FIA data and build that synthetic fuel set. Okay. Our partners and us recently got funding from the National Science Foundation in a project that is called Wi-Fi Commons. And one of the tools they're developing is called Burn Pro 3D. And this is at the San Diego Supercomputing Center. Okay. If you click on that link, you'll see a map of the US. And if you go to the upper right, there's like a map menu. And you just have to make sure that the Forest Service Fast Fuels 3D data theme is turned on. If you do that, you can find an area. The best areas to go are areas where you know there's forest. They show up as kind of green on the map. And then you'll see an interactive 3D viewer for these voxelized fuels. So by basically running our fast fuels program over the whole country, we've generated a data set of voxelized fuels at 1 meter for the entire country. And you won't be able to access this underlying data, but it's in there in the system. Each one of these trees has attributes. And of course, those are coming from the FIA plots. But what that enables you to do is interact with this as if you had a complete inventory of trees out there. One of the important applications to do with this is to connect this data to fire models. In this case, you're looking at QuickFire with fast fuels data. So QuickFire is a fast running 3D fire model developed by our colleague Rod Lynn at Los Alamos National Lab with strong partnership from Scott Goodrick and the Southern Research Station and several other partners. What you see here is this is fuel consumption, fuel moisture loss. This is vertical energy transfer to the atmosphere. And this is the resulting plume, and you can't really see them, but the surface wind vectors are represented here as little arrows that you can hardly see. So this is an example of one 3D model that we can connect this data to. And we're currently building fast fuels to really support running this model. But the goal is that we want to support all of them. We really want to give all of the models a space to be run. And so right now we've done QuickFire. We're working on a connection for high-grad fire tech. The next one on the list is WFDS and FDS, and including the fast-running FDS level set version. And then we have a great interest also in building a connection from this modeling to WRF S-Fire and other similar models that are coming from that family. But I really just want to extend a welcome to anyone who's developing any fire modeling that we would really love to be able to support your model with this system as well. So the goal is to try and take some of that work and make it easier for people. So from here on in the talk, I talk about some ongoing developments that we have going on. So the first thing is, obviously, there's a really substantial need for model evaluation, but this has also been extremely challenging because we don't generally have the data to run these models. And historically, there's been almost no funding given for model evaluation, and generally no funding really for model development either. I mean, I guess that's not totally true. There has been funding for model development, but it's easier to get funding for model development than for model evaluation. But model evaluation is a challenging task. So one of our goals with this is to make that easier to do. And the next one I'll talk about is this on-ramps concept. So if you refer back to fast fuels being a super highway connecting fuels and fire models, the on-ramps are ways to bring in different fuels data. Then I'll talk about some of the components we're currently working on, including this ability to run detailed fuel treatment scenarios, leveraging the FVS model. And then our plans for integration with current systems. And then a little bit about visualization and training. And I hope, if I'm not too slow, that we have time for discussion. And I think we should. What I want to talk about now is this building capacity for model evaluation. So model evaluation is really challenging because when you get down to it, what you need in a field scale fire or in a lab scale fire, it's easier because you can control many of the inputs. But in any case, in any model evaluation, what you're trying to do is take an integrated data set of the things that were going on at that time, run the simulation, and compare them against reality. Going back to our work in the Cycan Marsh out in Oregon, and we have a site in, sorry, I should be clicking, in Montana called the Bandy Ranch. So we're collecting data on fires. We're using drones to get pre and post burn fuels data, and also thermal mapping during the fire. And I note that Miguel Valero is on this call. He's also part of our team working on that. He's done some amazing work with fire behavior metrics from drones and other sources. And then we also are collecting really detailed data with the terrestrial LiDAR scanning on the ground. And then we have a component of this work where we're doing lab experiments and sensitivity analysis. We'll be actually doing that next set here in May at the Fire Lab. And then finally, there's weather data. In the past, we've even had a SODAR out there. But mostly we've relied on networks of weather stations and anemometers. We will be burning at this site in Oregon this fall, and a few other sites in Oregon also this fall. So if you happen to be in the US and you want to maybe see if you can come join us, let me know. We often have room for other researchers. So anyway, just an overview of what we've been doing out at Cycan. So this is the state of Oregon. And this whole part of Oregon is vastly underpopulated. There's hardly anybody out there. They call it the Oregon Outback. And it's very deserty. It's high, dry desert. There's not a lot of water, so there's not a lot of people. And our site is here at the Cycan Marsh Preserve. It's managed by the Nature Conservancy, which is a non-government organization that's focused on conservation. We have so far been burning at the north end of that preserve. So we did in 2017, we did these units, 2018, we did these units, 2019. We have more planned for this year that are going to include some of these units that we burned in 2017 and some other units up here. And just showing a little bit about what we get with this drone data, in case you're not familiar. This is looking at a standard NAPE image aerial photo of one of our plots. So this plot is 100 meters on a side. And if you zoom into the normal aerial photo imagery, you can see that you start to get confused, particularly in RGB, by the tree and its shadow. And if you look at it with what the drone sees, you see just incredibly different detail. And you can continue zooming in. In this case, the imagery that we're getting from these drone flights is about 4 centimeters multi-band. And in this case, this small square is 10 meters by 10 meters. And these two markers that you see here are the corners of a 40 centimeter square, okay? We're using a super high precision GPS to nail all this down, which is really critical when you're trying to co-register high resolution imagery. But I just wanted to show really quick that if you're not familiar with this, you can take a series of images with the drone and you can throw it through a process called structure from motion. And this gives you a point cloud that you can then derive 3D models of the scene with. So we're getting this pre and post burn. And in this case, you can see that the forest is not very dense. This is ponderosa pine forest, but in many cases, if you look into it, like right here or there, you can actually see the tree stem because of the oblique imagery, and you can go into the point cloud and actually measure that tree diameter, which is pretty cool. And these holes that you see at the edge are voids because they were outside. They didn't get multiple perspectives that were used to build that point cloud. And this animation was actually made with only half the data. So if we included all of it, some of those would probably disappear. But what we've found with this drone stuff is that 40 minutes of drone flight will map about 2 hectares of forest, every tree mapped and everything else, which becomes an incredibly good deal. It's still essentially a sampling when you're looking at the larger landscape, but it enables you to capture the fuel pattern pretty effectively. And most of the work is done by the computer once you get back to the lab. So anyway, so we've been collecting that data on fuels, and then here's just a little bit on what we've been doing with the fire stuff. So in our 2018 burns, we had 8 of these drone-centric data sets. And here I'm focusing on one. And this was on the edge of the marsh. So here is a big grassy area that drops off into some pretty wet marsh ground as you get farther out there. And here's what this looks like from the drone. So this whitish fuel is actually cheatgrass, which is an invasive, highly flammable, very light grass. Okay, this is a stringer of ponderosa pine, and this is some scabby little sagebrush over here. Okay, so these aren't exactly like really fuel heavy sites, but the cheatgrass in this case was really good fuel continuity. So here, zooming in, this is the here you'll see there's a couple small trees that I've just circled, and if you then look here, those same trees are highlighted. This is in the thermal imagery from the drone. So the drone is, we're lit the outside of the plot and we let it burn in, and we're getting thermal imagery at roughly 1 hertz, which is really extraordinary data. And one of our partners, Chris Moran, has been developing tools. So the imagery is flipped around because it was actually not oriented north-south in the previous thing. But here you can see some of the example work that he's been doing. And of course, Miguel Valero has also done some really excellent work. So there's a whole field of how do we take this data and really understand what happened. That represents the kind of determination of the real world true case or analysis thereof, which provides the basis for analysis with what we get with the simulation. So that's a lot of what we're focusing on, is building that capacity. Okay, my next little theme here is about this on-ramps process. So again, thinking of fast fuels as a superhighway connecting fuels data to fire models. These on-ramps are different ways to incorporate different data. So essentially, fast fuels is creating these synthetic fuel beds that are built off the FIA data. But when you have the in this case, ALS imagery, you can basically just replace that with the real positions and attributes for that area. So it's a little bit like when you're writing a paper, it's easier to edit a paragraph that's already written than it is to write it from scratch. So the idea is, with the data structure already in place, it becomes relatively easy to take any data source that can produce a tree list and replace the synthetic one with the closer to real one. And this is becoming more and more feasible because we now have a very rapidly proliferating field in remote sensing and use of artificial intelligence for classification. And in this case, there was some imagery that essentially demonstrated the use of AI approaches to map every tree and get individual attributes. So that kind of thing is increasingly easy to do from a wider range of sources. And our concept with fast fuels is that we really just want to make it possible, whatever the data you have, to make it useful in mapping fuels. So on the LiDAR side, so this line here is, below it are things that are on the ground, okay? And above it are things that are not on the ground. So finest detail, TLS, terrestrial. Then you have airborne LiDAR scanning, and then you have there's a spaceborne LiDAR called JEDI. All of those can be used to develop inputs. On the imagery side, similarly, UAS is giving us super high detail, 4-centimeter resolution imagery for small areas. And then we have things like aerial photos and satellite-driven data sources that can also be used. So what we really want to do is build on-ramps for all of these things. But so far, we're working on these two. The ALS and TLS are the ones we're focusing on right now. Okay, so some of our systems development, we've been making a ignition tool that enables you to run quickfire right now, but it'll work with the other models going forward, with a variety of different patterns for, kind of general approaches for prescribed fire ignition. And here is most recently, last month, they did a real burn in Georgia at Fort Stewart, and here you can see the data from a weather station showing the variability in wind. And here the points that you're seeing are helicopter GPS ignition points. So this is a simulation driven by data on the ground. And of course, we're still working on the whole evaluation of all that, but you can see that this provides an ability to both carry out a very detailed ignition pattern, capture variability in weather inputs, and then if you're mapping it with a drone or other stuff, you can start to have a basis for evaluating a model over space and time against real data. And then this is just an example of one of the metrics that would come out of that, which is just looking at the maximum power that was put out at each pixel. So right now, what we have built is the Fast Fuels API and the Quickfire API. These are all APIs, so they're all cloud-driven. They will all talk to each other. Things with dashed lines are ones we're working on. And you're going to see there's way more than we're working on than we actually have done. So these ones are pretty done. Then we are starting to work on an FDS API. We'd like to work on this. We haven't started yet though. But then other ones, these are the on-ramps. So we've got on the LiDAR side, we've got JEDI, ALS, TLS. These ones are in progress. We're starting to work with these. And then the other components that make a fire happen are ignition, fuel treatments, and weather. So all of those are going to be components that feed into this. And the important thing is that the whole thing will be run with ensembles. So you'll be able to take a case, run it through multiple fuel treatments, run it through multiple ignition cases, run it through multiple weather, and start to build enough data from a simulation point of view that you can start to provide information for managers across a wider set of conditions. So another thing that we're working on right now, and this is part of the fuel treatment scenario tool, but the fact that we can represent the trees with individual detail means that we can get at some of these more complex disturbance processes like beetle attacks, which are themselves complex in space and time. The beetles typically, the bark beetles, result in trees where they can no longer, they dry out, among other things, okay? And there's a period of time when they still have their needles, but the needles are super, super dry, and those individual trees are very flammable. And it's the mix of those that poses a challenge for models that assume an average. So that is a really important capability. Toward that end, we're building the tool. We had a connection with our Standfire between the modeling and FVS as a model to manipulate forests, but we've had to reconfigure that considerably to make it work with this new setup. But the idea is you'd have you know, an overstocked stand, you could do some thinning to it. And you could also, importantly, simulate growth over time, which is an important part of this particularly when you're looking at landscape dynamics. In terms of integration with our current systems, we're in mostly a discussion phase right now, but the basic idea is that if you're working with IFTDIS, which is the Interagency Fuel Treatment Decision Support System, you currently have these 3 tools that are Rothermel-based tools. And this one is basically FlamMap. This one is the MTT version of Farsight, essentially. And then this is like FS Pro, okay, which is an ensemble approach. We would imagine that we would just have another menu where you could add 3D stuff. And then from there, all of the different models that we start building this for would be available. So the goal here is, again, to support all the models that are out there. And as part of this, we would envision a tool that would enable comparison between models with the same inputs, which would be very useful in terms of understanding the strengths and weaknesses of different models. Okay. And then finally, I think this is my last theme, but so one of the advantages of going to 3D is that you get an ability to use 3D to more intuitively describe a situation. So you're probably familiar with FDS. This is an example FDS simulation. The fuels come from fast fuels and the topography from fast fuels, okay? And here we have a simulation going. And you can see, you know, the smoke plume going over the landscape. And obviously, this tool, SmokeView, has been developed for a long time and is very widely used by users of FDS and has all sorts of amazing capabilities. What we wanted to try with this was seeing if we could take that simulation output and make it accessible to a user in the context of a VR environment. So what we've done is we've translated the 3D fire model output into a VR, and it's now possible for a user to walk through that scene and look around, see the fuels, see the fire behavior. In this case, you can see that we're representing the trees as relatively simple, low polygon 3D objects. They kind of look like folded paper, but they're still recognizable as trees. So that's a concession to not wanting to slow it down too much on the visualization aspect. In this case, where the fire is and the intensity that it has is coming from the model. So this is just reporting back science data from the model, but it's being represented as a more visually compelling thing using the, in this case, the video game engine Unity. We can also represent smoke with this as well. Anyway, this is an ongoing thing, but we're really interested in continuing to build this capacity with the idea that fast fuels would enable you to generate this kind of output for any simulation as an automated process. So anywhere in the country where you were doing a fuel treatment, you could run it, get output, and then put it into a thing like this so people could walk around and interact with it. One of the things that you can do with this kind of game engine is you can start to play with different levels of detail. So here's a planimetric view of a plot where they did some thinning around some trees. And here's what that looks like if you use a really detailed 3D model. So the people who work in the video game industry are pretty good at representing things like almost as realistically as the real world. And this is an example of using that kind of technology to make a more compelling visualization. It's not necessary from a scientific point of view, but when you're trying to work with the public, it's very nice to have visual stuff that is intuitive, that they can kind of relate to. You can also represent fire, burn trees and things like that. So this is another example of the kind of visualization that you can do with these packages. So that's the end of my talk. I think I ended with a little bit more than 10 minutes to go. This is a view of one of our burns out at SciCan, an oblique view from a drone. So anyway, yeah, I'd be happy to take any questions.
That was awesome. Thanks, Russ. Uh-oh, I'm getting some feedback. I don't know if that's on my end. Everybody on mute. Hopefully. Okay, I'm still hearing myself, but so maybe I will be brief and let people ask questions. Russ, there's already a few of them in the chat box. Oh, that's better. So yeah, I just want to just point out, like this is really interesting stuff, particularly for those of us in the Forest Service, right? Because the Forest Service recently rolled out their 10-year strategy to deal with fuels, and a lot of it has to do with fuel treatments. But as Russ points out, the models, our operational models that we have right now really have not been set up to deal with it. So this is really like the best way forward to be able to like look at how fuel treatments actually affect fire behavior. But we need input to those models, and fuels is especially one of those big things that that we don't have. So this is really like encouraging work in my opinion, and I'm pretty excited about it. So Russ, you got a couple questions here in the chat box. I'll just start reading them off here if you'd like.
Sure.
The first one is whether the TLS and UAS data is available for the continental United States, or is there a plan to do so in the near future?
Okay, great question. So neither TLS nor UAS data is likely to be accessible for the whole country ever. They're both very detailed. So I think they're more likely to be better thought of as detailed plot data. Okay, so similarly to how we're representing plot data at a landscape scale with fast fuels, the data that we collect from TLS or UAS are likely to help us inform how we model the detail, and it provides a ground truth for a small area. The more you have, the better, right? There is an ongoing effort that's now getting to be popular. It's still not very far out on its plan yet, but there's a multi-agency effort that's using TLS for fuels monitoring. So similar to the kind of plots that you would normally do to go through a forest and look at inventory, these TLS things are so fast. Like we have a crew at the lab, and if you run it for 3 minutes, it is mapping everything in 3D for not a huge area, but the detail that you get on the fuels in that is extraordinary. So I think of both TLS and UAS as complementary plot enhancing data. They're still ground based largely. I mean that the drone is flown from the ground, but they like the UAS is maybe the important scale jumper, because you can go, you can do multiple hectares in less than an hour. And that lends itself quite well to getting a fairly large population of tree measurements that can be then used to scale up to larger areas. Okay, now as far as ALS data, the airborne LiDAR, we increasingly have vast areas that are mapped wall to wall with ALS. We still don't have it across the whole country, but some states are mapped in their entirety with high resolution ALS data. So we plan to leverage that. But the bottom line is that for our purposes, we want to be able to provide wall-to-wall data as best we can. And if we have multiple data sets that have recently been collected for an area, we want to be able to leverage those. But we still want to have a baseline strategy to provide something so people aren't limited by data. So that's essentially what our strategy is here with the on-ramps. All right, maybe we move to the next question there.
Okay, yeah, sure. As I say, that also brings up your point about how quickly the fuels can change, right? So if you need to constantly be running a very high intense method of mapping your fuels, you're not going to be up to date as easily, right? So that's where blending the different methods probably will be important, even going forward.
Right, and in addition to that, having the capacity to model the vegetation forward in time is really critical to that as well, because ultimately any mapping effort is typically going to be limited in spatial extent and to a particular time. And if you want to have a kind of up-to-date overview of stuff, you have to have a way to bring them into the same time frame.
Indeed. Okay, so the next question is from Vito. He says, it seems to me that the utilization of these models is quite prospective, something in the future. What is the current situation with regards to actual usership? And specifically, he means not academic, but for management or incident response purposes.
That's a great question, Vito. Thank you. Yes, at present, the use of these 3D models is completely prospective. There's no real managers using them, but like you could see that we just collected data for a real world prescribed burn that was last month, and we already have a model of it, of that. So the tools that we're building in this framework are going to make it increasingly possible for people to run these models in advance of their management on the ground, which is another important aspect in terms of validation. When we use models to make predictions, ultimately, we don't expect to get everything 100% right, but we want to be able to assess an accuracy and say, are we 70% right? Are we 10% right? Right? So having that the ability of these modeling to do that beforehand, we're starting to work with management users who are going to be our early testers, and we have identified a series of locations in the U.S. where people have real-world fuel treatments or prescribed burns that they're planning, that they want to work with us on, and we hope to expand that. But at present, it's a handful of locations. That my sites in Oregon and Montana are really good test beds because we're capturing the data ourselves. But we're going to work with these folks in different parts of the country on these fuel monitoring projects where they're using UAS and TLS to collect data and coordinate with them as well. Okay, maybe on to the next question there.
So the next one's from Miguel Valero. He says, this is amazing work. He has a question about the scalability of high-resolution drone-based 3D fuel mapping to landscape scales. Do you think that these techniques could be adapted to fuel maps using airborne sensors during or shortly before landscape scale wildfires?
Yes, I do. Yeah, and I think that what becomes the challenge is the closer you get to real time, that gets tricky. But certainly airborne data sets are very capable of delivering very high quality 3D fuels maps. And, right now, as you know, most of the effort in the, near ops part of the U.S. Forest Service, incident management stuff is about collecting thermal IR data on, active fire incidents. But if that was combined with high resolution imagery, it could be a standard product that we get that data processed out to very informed fuel maps pre and post. So that would be a really important capacity to develop. And in fact, I've been in contact with people who run the imagery programs, and I think that we'll see some interesting things going on there in the next couple of years.
Yeah, it seems to me that even the use of UAS on actual fire incidents right now is a fairly new thing, right? And so there's a lot of just trying to get comfortable with the idea that they're there and using things and doing things, right? And so hopefully, as they're around more and more often, we might be able to use them more and be able to get more information because we'd be able to fly more often and fly more of them and do more things with it. So I think we're kind of in a transition stage, I think, with the UAS right now, it seems.
Right. And one of the really critical uses of UAS on a fire incident is for safety. They are incredibly useful as a lookout. They're the ultimate lookout. They're also very, very useful for spot catching. In fact, we did that in 2017 on our burns at Sycan. On one of these burns that you see here, we had a spot that jumped into grass, adjacent to the unit, and we actually used the drone to see where the spots were to help us put them out. So, yeah, and then the whole aspect of just having that eye in the sky to keep track of people. And you can imagine that in fact, the military has already been doing this for a really long time, right? But they have they have a drone and they have an AI that can link to troops on the ground, and they can identify friendly versus unfriendly. And that has a big effect, as we're seeing right now in Ukraine. I think ultimately drones are an extremely powerful tool for resource management and fire. And right now, the Forest Service policy in our country is quite constraining about the use of them. For example, Sarah and I are not allowed to use them. But we work with academic partners who do, and it should be the case that soon that we do have that. And I think there's just a whole lot of opportunity for innovation that takes advantage of those platforms.
Yeah, I completely agree. I mean, I think the future for drone use in fires is going to be very different from 5 years from now than it is now. So that's really awesome. I mean, we are coming down on time here. If there are any other questions, feel free to unmute here. Beto complimented you on your exceedingly well thought out presentation. So again, yeah, that was very well done, Russ. So thank you again. I'll give people here just a second to ask questions if they have them.
Excellent. I see Alex is typing a question.
Yes. Oh. Yes. Thank you.
Thank you very much, Alex.
Well, of course, I mean, I have a billion different questions, but I can ask my questions to you at any different time. So I suppose we have 1 minute left, and I'll use that minute to, again, thank you very much, Russ. It was a fascinating talk. It's always good to hear you talk, and it's been a while for me too with COVID. Haven't been able to see you recently, so very glad you were willing to do this and put together this talk. So thank you, and thanks everybody for coming.